Hey guys, my name is Cole. I'm here to talk about the level select and the home screen for our card flipping game. Um, I'm going to start with the level select code, and as you can see here, you have your inputs, which are the clock, the reset, and then what level you are on. And then the output is our 48 bits, so it's 0 to 47, which makes it 48 bits, which is 16 tiles, and then 3 bits for each tile. When we started it, we originally did not have the code hard-coded, but we ended up hard-coding each individual level. So we set up the game by taking all 48 bits, and then you can level select through either 0, 0, 0, 1, 1, 0, or 1, 1, and those are each game. So then it will iterate through our hard-coded sequence. So as you can see, it says 3'D, so it's in decimal, which is base 10, and we decided to do that because it allows us more colors, and it allows the user to add more colors rather than just picking 1 or 2 colors. So as we go to the home screen, you can see where the level select comes into play. So again, we have our inputs, which are our clock, our reset. But what's different is we have our level buttons. So there's 4 buttons on the FPGA. And so it's 0 to 3, which gives us 4 inputs. And that just asks which level it wants. So previously on the level select, I showed you that there was 4 levels, and each button has a different level for the FPGA. The outputs are what level, and then the output would also be to start the level that you selected. So it's outputting the correct level. The code then activates the level and starts it. And as you can see on line 17, it says if it is greater than or equal to. So as I walk you guys through 0, 0, 0, 1, 1, 1, etc., that is where you get the level. So it's just checking if it would be even a correct level to be testing. And then as we go down through the code, you're just checking if it's the right code, and then the game logic comes into play. So it's updating the game and the buttons depending on what the user is selecting through the FPGA. And then it goes through each level, and it's making sure it either starts or doesn't start. And then at the end, if it's activated, or it will reset. So that is how our level select and our home screen are integrated into our game on top of.
One is a very simple one. It's the debouncer module, which is used to debounce switches, buttons, and other inputs. This uses a finite state machine to make sure that the input is correct and bounces the signal back to the digital logic. This is very important, although simple, because it makes sure that the input stayed high, like a switch state when it's high is actually high, done by the user and not noise. The next module I'm going to talk about is the VGA driver, which has 5 outputs, VGA R, G, and B, which decide the pixel color of red, green, and blue, which can decide any combination. The VGA HS and VS, which is the vertical state and horizontal state. The VGA driver uses 2 state machines, a vertical state machine and a horizontal state machine, to determine pixel placement and the state of each pixel. We can see the horizontal state is used to get the pixels in the horizontal state and the color of it. And then it divides our VGA, our screen, into 16 places of a 4x4 grid of tiles. Those tiles are then, the color behind the tile is then revealed from gray, which is the default, to the color that it is based on the value when the switch is pressed and the game state input is high. Once the game state input is high, then we get a case statement deciding the color of our tile. Then uses the vertical state and horizontal state machine to keep it in that state and switch it back. The next module I want to talk about is the LFSR random module, which is a module we would use going forward had the project we had more time. This is a module that randomizes an array to create a pseudo-random number. This module is then used in the array shuffle module, which would be used to get an output of 48 bits. So we can have a flat array, 16 times 3, since each value is 3 bits of our values. And this would make it random so that every level you play or every time you reset the code, it's a new game.
I mostly worked on the game logic file and the main file implementations for this project. Here we have 3 inputs, one being the clock, one being the reset, and a 16-bit switch. And we're supposed to output LEDs, which are supposed to indicate the game state, and the output tiles, which we made 48 bits because we ended up extending it by multiplying the amount of switches with the amount of bits each tile is supposed to carry. So as we go on to the always block, we start off by resetting the game, which is basically just setting everything to like its default standing. And then after, if you don't press the reset, if it's false, you would go on to like the actual game logic where so you would first start off with the first if statement where you input the first switch, and then you check with whether or not the second switch has been selected. And this statement is not select 2 and state I is equal to 0. So that means that you first flip the first switch. So you would set that equal to I, and then you would set the second select equal to 1 because you still need to select the second switch. And then after that, if the second switch has been selected, you would set it equal to 0 because you would no longer need to select the second switch in order for the tiles to start matching. Set that up. And then inside the else if, we have another if statement where we get the bits of the first selection and the second selection, where we start comparing them. And if they both match, we'll set them equal to 1, and both LEDs for the first and second switch will start to light up. And if they don't match, we declare it to be a mismatch, and we set that mismatch equal to 1. And then at the end, we would just reset the states. And finally, this else if statement we have here, this one was meant to like if you switched it back to like its off state, it's supposed to get rid of the colored block on the screen. We never really got it to work properly, but according to the game logic, it's supposed to reset the original tile once you make the input for that specific switch 0. And lastly, my other implementation was the main file. Here we ended up we had like 4 inputs and a lot of outputs, especially with the horizontal sync, the RGB, and the vertical sync. And I mostly implemented the clock divider, the bouncer for the buttons, because we had too much noise when we didn't have the bouncer. I implemented the home screen, the level selection, and the game logic.
Alright, so I'm going to be talking mainly about the score because that's what I kind of focused on. There's obviously some other things that I touched upon, but the score was definitely something that was a thing. I also upped on the tiles a little bit with the constraints file because there's some errors there. But so let's talk about our score counter. So the way our score works, we made it so that it's just based on the lowest score possible. So it just increments by 1 each time. So you just have to get the lowest score possible. I'll talk about this more in the demo about like how it should have functioned, or like it does function correctly, but how it would function if the game fully worked. But so We have our clock, we have our reset, our anodes, and then our cathodes, just the LED out. So, because it's the 7th segment, we have 7, but the anodes, I'm only using the 4 rightmost digits. So, display number displays the number, obviously. The refresh counter, it just refreshes the rate that it should be outputting. And then LED activating counter just shows if it's actually counting and repeating. So, if we keep going on, we have so what we have for this part of the code specifically, this is basically what increments the number by 1 based on the clock. Then this is the refresh counter, so like it keeps refreshing it. And then this is the anode that basically activates the signal for 4 LEDs with a digital period of 2.6 milliseconds. And then the decoder, which basically says like the tens, hundreds, and thousands digits, and also ones digits. And then so this is the patterns for 0, 1, 2, 3, 4, 5, 6, and then you also have a default for 0. Alright, so this is our 311 project, the memory tile game, that you're supposed to select tiles and match them, and if they don't match, they would technically reset to the last state, but we're having troubles with this, as probably stated from my teammates. So the score increases, and you're trying to get the minimal amount of score. And if the game was fully there, when you would mess up a tile, it would take you more time because it takes you back to state. So you're trying to complete the game as quick as possible. So like if you had 2 reds on the screen, like you matched 2 red tiles and then a red and a green afterwards, then it would reset you back just to have the red and red until you got like you're losing time theoretically. So if you look at the screen, so I have a red. Then I have another red, and you see that like they match, it's good, right? And then if I click another switch, I get another red, that's good. But if I flip, I get another red, so I'm getting lucky right now, and I would still stay in this state. So if we keep going and flip some more switches, you see I get a green. So now in the next color, we get a green, which we're getting really lucky actually, which is kind of crazy. And then so we keep going. We get a red, so we try and match another red right now. Oh, we got a green. This will reset the game, which we can do. And then, but first, if you look back on the board, you see the score still increase, and the LEDs light up, so the ones that they match up. So, if we turn on the light, if we reset the game will blink. And like, it shouldn't reset you like that, but it does reset you to the last state. So if you can remember what switches you flipped, it can stay the same, because like level 1, 2, 3, and 4, they're all hard-coded so that you would remember which tiles are which.